right, so we're very happy to welcome Phil Lewalle to our IQS seminar series this week. So let me give a brief introduction if you don't know Phil already. So he did his undergraduate studies at the University of Rochester in New York, and then followed with his PhD at my group there at the time, working on topics in continuous quantum measurement theory, in particular doing a lot of work on multiple most likely paths and chaotic paths, and then also later on in his dissertation, working on entanglement by measurement, different ways of realizing that with different types of continuous measurement protocols. So after that, he graduated and got his degree, and then went over to UC Berkeley, working with Birgitta Whaley, and now is recently, or is coming toward the end of that postdoc, and he'll be telling us about some of his work today about the quantum Zeno effect and using that for multi-qubit gates. But if you didn't know, I would also mention that Phil is also a very accomplished jazz pianist, and so if you haven't heard him play the piano, you have to get him to play for you sometime. So Phil, I'm glad to have you here. So glad you came down to Southern California. The floor is yours.
Thank you for the kind introduction, Andrew. I'm very glad to have been invited here and share this work with you today. So what I want to tell you about today is some work that started between some of my co-authors in Berkeley, in which I sort of inherited and have now helped to see over the finish line. I'm going to mostly emphasize the theory side of the work, but I will at the end briefly mention a related experiment done in Shay Hacohen-Gourgy's lab now at Technion. So the gist of this work is about using the quantum Zeno effect to do a non-local kind of gate based on using only non-locality in the measurement. So I'll split this talk into sort of two parts. The first 10 or 15 minutes will be largely conceptual. I'll illustrate the scheme of how we sort of turn a boring unitary drive into a non-local gate using the Zeno effect and give a sample system. In the second, longer half of the talk, I will spend some time focusing on how we actually engineer the interesting sort of measurement that we need in order to accomplish this. So let's start with the Zeno effect, which I think most of you here are familiar with, but we can read this fun little blurb. So this is Zeno as recounted by Aristotle, as recounted by Wikipedia. If everything when it occupies an equal space is at rest at that instant of time, and if that which is in locomotion is always occupying such a space at any moment, the flying arrow is therefore motionless at that instant of time and at the next instant of time. But if both instants of time are taken as the same instant or continuous instant of time, then it is in motion. Okay, so what we have here in very old-fashioned language is something which we might now with a contemporary lens recognize as a sort of primitive idea that would later be formalized into calculus. And also this sort of idea that, this arrow is in motion, but if we look at it at very specific instants of time, we might imagine that it's not actually moving. Now, the reason I bring this up is that this Zeno's arrow paradox has entered the quantum lexicon in a somewhat different form. So in quantum mechanics, the Zeno effect states essentially that one can use strong measurement to inhibit unitary dynamics. So one can imagine that we have some Hamiltonian that a system would follow when left alone. But if we do sufficiently strong and frequent projective measurements, we will collapse it back to an eigenstate. And if we do that very quickly, then we will essentially not let the system evolve and always collapse back to the state we started out with a probability of very nearly 1. So this is the quantum Zeno effect. We can essentially freeze a system's dynamics by observing it. Canonical interpretation. So how might we go ahead and use this to actually do some interesting quantum information operations? I want to sort of expand the Zeno effect to a larger system. So let's imagine that we have some larger quantum system and there's some unitary evolution going on that for whatever reason we might find boring. Something simple happens when the system is left alone. The idea behind this gate, broadly speaking, is that if one can engineer some kind of measurement, leaves a subspace of the system alone, but does interrogate some other space, then essentially we can use the Zeno effect to freeze transitions between subspaces and perhaps be left with some dynamics in an unobserved subspace that are much more interesting than what we started with. And in the limit of frequent perfect projections, we can define some effective Hamiltonian in the subspace based on the projectors associated with this measurement. So I'll develop the example that we're going to consider for the majority of this talk. So let's imagine I have a Qutrit and a qubit. There's going to be no direct Hamiltonian interaction between them. Anything that happens to them both is going to be because of joint measurement on the composite system. So I've drawn this two ways here. This is the same system. Now I'm going to apply some trivial boring Hamiltonian. In this case, that's going to be, I'm going to drive rotations between the E and F states of this Qutrit. So that's going to be the only unitary thing going on in this scheme. And the idea here then is to make a measurement which interrogates a non-local property, specifically whether the composite system is in the highest excitation state or not. That is the question we want to ask. So the idea with that then is that we will non-locally block part of this Qutrit local unitary and come up with something much more interesting now in this remaining subspace. And the idea will be to do essentially complete rotations that start in the 2-qubit subspace and end in the 2-qubit subspace and do an entangling gate using this boring unitary and then this very particular measurement. Okay, so I can write down what this looks like in the sort of projective limit, right? So I have
maybe a quick question.
Please feel free to interrupt.
In the last sentence, you said the 2-qubit subspace, but if you remove one level from consideration, that really gives you 5 levels, not 4. So why do you say 2-qubit?
I say 2-qubit because we're going to initialize states populated in these 4 and then do complete rotations with the idea that something, whatever is here will have gone here and then come all the way back.
All right, so then you're trying to exclude GG from the analysis.
No, we will use this 5th level, but it's going to be auxiliary. We're going to consider a gate that starts in the 2-qubit subspace and ends in the 2-qubit subspace, ideally, if we perfectly block all of this.
So those middle 4 then are your 2 qubits.
FG will be used only in an auxiliary capacity. So these 4 will be the start and end of the operation if we do this properly. Okay. All right, so we can get our effective H-Zeno sort of in the 5 levels by projecting out this state we want to forbid here. And what this will do then, right, if we do a complete rotation, is that we'll get an entangling gate here that maps, as it turns out, like an equal superposition onto a Bell state in the 2-qubit subspace. And this is locally equivalent to a C0 or a C-phase gate in that 2-qubit subspace. So by locally equivalent, I mean the action of this on the 2-qubit space is equivalent to these other operations up to just some other local operations, as shown. I also want to point out, although I won't focus on the larger system, the scheme does actually scale 2 more qubits. So if you have a Qutrit and n-1 more qubits, if you can apply this composite measurement, you're basically doing an n C phase that entangles all of them. Okay, so let's start shifting towards what will become sort of the practical emphasis of the talk a little bit. I first want to point out that the Zeno effect is something which does occur on average in Lindblad dynamics. What that means is that while we talk about the Zeno effect as something that arises from measurement, we can in some sense just consider engineering dissipation. Whether we actually read the measurement outcomes or not is on some level extra. Dissipation is enough to make this happen. We can get a little deeper in that by just considering a qubit model and looking at sort of escape through the Zeno block. What's the probability given some continuous dissipation mapping to a forbidden state? What's the probability of sort of our unitary breaking through? And you can make reasonable approximations and wind up with something like this, right? Where I'm using an effective qubit model for sort of the gate subspace and then a forbidden state I'm measuring. One thing you can do here, I won't go into the details, is look at the effect of actually measuring versus just dissipation. And that's perhaps best summarized here. If we look at sort of the fidelity of the block, I can look at just Lindblad dynamics. So just dissipation of this blocking observable, as compared with a case where I actually collect some measurement information and therefore have a herald of whether this worked or not. So I make some post-selection and look at the cases where my measurement, to the extent that it can, tells me I did not go through my Zeno block. Right, so I'm plotting a fidelity here against basically the ratio of the measurement strength to the unitary. And I can see that both of these dynamics approach the Zeno limit of perfect blocking, perfect gate fidelity as the measurement gets stronger. But the heralded version, the one where I actually do the measurement, does approach that limit faster. So for the remainder of the talk, we're mostly going to focus on the Lindblad dissipation for simplicity. But I want us to do that with an understanding that that is in some sense lower bounding what you could get, and you can do better by actually reading your measurement outcomes in individual runs of the experiment.
What are you measuring here?
In this case, you're imagining that you have maybe some scheme where a photon would escape into some continuum of modes and you herald on no jump. One could think about doing other measurements as well and how to map that post-selection on.
What do these two rates depend on? And the fidelity going, like what's the scale of the convergence in these two cases?
I believe they're both exponential. I don't remember actually what how the heralded one is modified. It's just a slightly different rate that asymptotes faster. We could talk offline with the paper later if you want.
But I guess the unconditional dynamics just also includes the jump cases as well, compared to the red line.
Yeah, the unconditional dynamic, yeah, you're just averaging over it. Yeah, that's Zeno effect by dissipation without checking if it worked or not in an individual case. Okay, so from here on out, I'm going to start imagining that we're going to do this joint measurement by placing our Qutrit and our qubit in a common cavity and using that for readout in some way. And we'll increasingly get into the weeds then about how to actually realize this measurement of just the highest excitation number. So there's sort of two schemes I'll consider here. One is a longitudinal coupling, the other is a dispersive coupling, and the general trajectory here will be going from something still quite idealized for theory purposes to see what we might like to engineer someday versus what is possible today in superconducting qubit systems. So we will get gradually less ideal and more realistic as we go. So what I just showed you with the Lindblad dynamics, it implicitly assumes some kind of direct system environment coupling and either monitoring or averaging over measurement outcomes over successive time steps. I want to contrast that with the case we're actually going to want to consider. In this case, where there's sort of this cavity degree of freedom interposed between our, in this case, 6-level 3x2 system here, and the output line where a detector might actually collect something or where information is permanently dissipated. Okay, so this is going to be the general scheme we'll consider for both of the types of measurement I'll consider. We'll have sort of photon dissipation of the cavity into the output line. We'll be doing our boring unitary into the Qutrit, and then we'll also have whatever coupling between the Qutrit and the cavity is being used for measurement. So everything I will talk about for the rest of the talk is going to fit into this general scheme. There are a number of issues that we're going to spend that time unpacking here, right? So as I said, what I'm swapping out when I talk about different types of measurement is going to be the coupling here. Okay, so let's start by understanding some general properties of measurement with this kind of architecture. So I'm going to ignore any Qutrit dynamics on their own to start. So if I have a situation where this coupling Hamiltonian allows me to write something that's sort of block diagonal with the Qutrit only eigenstates, block diagonal up to just displacements and phases on coherent states, essentially, then what I'm going to be able to do is write my joint Qutrit cavity state in a very useful form, where I basically will have entanglement between energy eigenstates and some coherent pointer states. This is going to be something that we're going to use to get analytic results going forward, but we're also going to have to understand its limitations. Okay, so in that case, we're going to get measurement strengths between any given Qutrit transitions that basically go as the distance between the associated coherent pointer states, mediated by the rate at which photons are leaking out of the cavity to a detector. Okay, now let's reintroduce this Hamiltonian. Strictly speaking, in the purely mathematical sense, this ansatz is no good if I do something here that breaks my block diagonal assumption, which anything that's not, say, sigma z, not intrinsically diagonal here already on the Qutrit will do that. Okay, but that doesn't mean we can't actually use this ansatz in some useful cases. So my coherent pointer states under this kind of thing are going to evolve generically with some frequencies. Okay, this is in each Qutrit block, and approach a steady state. I'm going to denote that with the bars at a rate that's basically set by the decay of the cavity into the output line. Okay, so that's setting the decay constant here is setting a time scale on which pointer states will settle into a steady state, which we can use to get a steady measurement strength. So there exists a Markovian regime where we can leave this be and our ansatz will remain approximately good. And essentially what I'm saying with that is that if I do independent Qutrit dynamics that are much slower than this decay rate out here, then essentially I can still say this and have it be approximately right because my pointer states can sort of adiabatically follow whatever goes on independently back here. So in an ideal situation from a readout perspective, I would have cavity decay much faster than whatever independent dynamics I do to the Qutrit, and then I'm measuring on a time scale where the cavity has reached a steady state within any given time step. That will give me a consistent, steady measurement strength with time, and essentially allow me, because of the separation of time scales here and here, to forget that these two degrees of freedom were distinct. That gets me back to the sort of Lindblad picture, just monitoring the Qutrit that I originally had. Now, with that understanding, I think you can see that there might be some things that could go wrong here. So when I talk about non-Markovianity for the Qutrit, I'm always going to be talking about that with respect to the Qutrit. So everything I will talk about here will be Markovian with respect to the joint Qutrit cavity system. But if the cavity evolution and the Qutrit evolution interact in a way where that affects the measurement, I'm not going to be able to just forget about the cavity sort of memory interposed between the two. So this is going to introduce some timescale issues that will impact the dispersive scheme we'll eventually get to. So just to summarize, right, when I have this separation of timescales, my measurement strength approaches steady state, and I can forget about this. We will later be forced to deal with a situation maybe where we have some time-dependent measurement strengths. So I have interplay between the qubit dynamics and cavity pointer states. There might be some distortion of my coherent states. So that coherent state ansatz I used is going to start to become of limited value. And in the opposite limit, then I'm going to not have measurement at all. So there are two different reasons that could happen. If I reach this by making kappa very small, I'm basically closing the system. So there's going to be no measurement because it's just unitary stuff. My measurement strength falls to zero. If I get here by making omega very large, at some point, this rate is going to also become much faster than whatever coupling I might have here. And I'm basically at that point going to be doing something that looks like dynamical decoupling. My pointer states are no longer going to carry information about the qubit. So there's an isolated limit and a fast limit where everything I might want to do will fall apart, and we have to avoid that. Okay. So I'm writing just the qubit versions of these Hamiltonians for now, right? But I'm going to consider first this fairly idealized longitudinal coupling. So that supposes that I can connect sort of energy eigenstates directly to a cavity quadrature. This is going to let us do sort of an ideal Zeno gate, but under assumptions that are, I think, not tenable for experiment right now. And then we'll shift gears and understand what issues are raised by trying to use this more realistic dispersive coupling.
Phil,
Yeah.
So you say that you need that sigma g. That's not your ansatz, right? You have to have that diagonal in the qubit space.
Yeah, so both of these Hamiltonians fit this ansatz, yeah.
But if you use sigma x coupling between the qubit and the cavity, then your ansatz fails. Is that?
Yeah, well, so when we get to this, I'll show you that this is something that arises as a very particular sort of regime of the usual dipole coupling. This is an approximation that works under fairly specific circumstances. Okay, so this is the qubit generalization of this longitudinal scheme, right? So I'm imagining I can couple qubit eigenstates directly to a cavity quadrature and do this. So what do I want to do here, right? We're calling this Zeno gate now, right? I wanted to take a state maybe that looked like this, coupled to an initial cavity vacuum. And then I want this to evolve under this interaction into something like this, where my pointer states are going to let me do, right, this very specific measurement that only measures a forbidden state, but leaves the measurement strengths very low or vanishing in this other subspace where I want to do useful operations instead of decohere. Okay, so if I use my cavity model with the coherent state ansatz, in this case I can write down sort of steady state measurement strengths depend on, right, variety of coupling parameters. To use my sort of Markovian, the assumptions I want to use to do readout, really I just need this cavity decay rate to be slower than the bare cavity frequency by quite a bit, which is not a particularly stringent assumption, so we're going to make it. So what you'll get then is essentially measurement strengths that depend on the square, the square difference between the different couplings. And then you'll also get this resonator-induced phase, which appears in the literature. Right, so that's not within the coherent states. That's phase accumulation between different branches of the joint superposition here, which will accrue as goes like this. So, right, what I want to do with, if you recall, I have this Qutrit by qubit system. I want my transition, any transitions to the FE state to be monitored as strongly as possible and the others to be measured as little as possible, or ideally not at all. So clearly the best thing I could do then would be to make my coupling constant for this, the forbidden state as different as possible from all the other ones, and the other ones as similar as possible. So for instance, if I pick these just to have opposite signs and equal magnitudes, this is what's going to happen in my pointer state quadrature space, right? My forbidden state moves one way, all the others move away together in the opposite direction. And this is a very desirable situation, right? I've isolated this state without decohering sort of my operational subspace. And with this choice of opposite sign, I also kill this resonator-induced phase, which is nice to just not worry about. Okay, so I'm now plotting two figures of merit for the Zeno gate under this very idealized set of assumptions. So over here, I'm looking at what is the fraction of the population on the Zeno block transition, which fails to make it to the blocked state halfway through the gate. So this is a proxy for how well I'm Zeno blocking that transition. On the other side here, I'm looking at the concurrence in the 2-qubit subspace at the end of the gate time. Okay, and I can see here that I can pick some cavity decay rates where for the parameters I've chosen, I can reach good blocking and high concurrence generation. So these curves here are basically showing a gate that's working fairly ideal. Now, of course, what I had to do to get this right was to essentially suppose that I had some kind of coupling Hamiltonian that I used for readout, in which I put an intrinsic degeneracy to protect this space while blocking transitions to the other one. As we move towards dispersive measurement, which is the much more realistic case, we're going to have to use some other tricks. Okay, so this is the analog of the Rabi Hamiltonian for the Qutrit that I want to start with. So this is basically dipole coupling to the block, which, as Vivek noted, does not match my sort of block diagonal assumption. So there are two approximations that get us back to the dispersive thing that's typically used for readout in superconducting qubit systems. So on one hand, I need to make a rotating wave approximation. And then I make a further dispersive approximation, which has to do with the couplings and the detunings. What I want to point out about these, the details aren't so important, is that the dispersive approximation requires me to be, my Qutrit transitions to be off resonant from the bare cavity frequency, but the rotating wave approximation requires that not be by too much. So we need off resonance, but near resonance in the relative scheme of things. So sort of the frequency space we have to work in is constrained from both sides. Secondly, if I have very high photon numbers, I'm going to also have a problem over here with my dispersive approximation. Okay, so this gets us sort of the coupling with the block diagonal sort of form I was interested in. Right, but we've already had to sort of behind the scenes make some much more stringent assumptions about how we got there. Okay, so let's forget about the unitary on Qutrit for a moment and just now focus on the readout. So I have dispersive coupling to the eigenstates. And I'm applying a coherent drive tone, sort of supplying. Supplying the tone in the cavity that I'm using to do readout. This is in the frame rotating with this coherent drive tone. Okay, so I have this detuning. I have my dispersive shifts attached to Qutrit energy eigenstates, and I'm driving quadrature over here. So if I look at my cavity decay rate, and this sort of coherent drive tone. I need to quickly understand that if these are very unbalanced, for instance, if I put a lot more light into my cavity than leaks out in a given span of time, I'm going to have a problem with my photon number, right? So I cannot arbitrarily raise the scale of this parameter and maintain the assumptions that I made to have my dispersive approximation to begin with. Okay, now that is something we want to pay attention to, because if I just look right at the simplest sort of Markovian steady state measurement strength here, I again have right this squared difference between couplings. In this case, these are now the dispersive shifts, but then modulated effectively by photon number. So it's tempting to say, oh, I can just make this really strong by upping the photon number. Well, no, because the assumptions you made to get here will fall apart to begin with. Okay, so driving arbitrarily strongly is not an option to make strong measurements here. The second thing I want to point out is that these dispersive shifts, these chi's, they scale roughly qualitatively like Qutrit excitation number in practice. What that means is I'm not going to be able to just assign them an intrinsic degeneracy like I tried to suggest with the longitudinal coupling. So we're going to have to do something more creative if we're going to isolate one state that we Zeno block and leave the others alone. So the question for the next few slides is, right, I have all these different parameters going into this measurement scheme. How should I pick them to make a Zeno game? Yes.
Quick question. You're pumping at a particular frequency, but you have many resonances all shifting. What is the shifts ratio to the line width? And how does that?
That is the correct question. Justin is asking the correct question. Okay, so let's use our coherent state measurement model without any unitaries going on to get oriented here. So what I'm plotting here are steady state measurement strengths for all 15 transitions. So the ones to FE, the ones to the forbidden state that I want to block are in red, all the rest are in black. So the name of the game here is I want to make all of these red curves basically as big as possible while all the black curves are as small as possible. I'm plotting these measurement strengths as a function of the frequency of this coherent input tone as detuned from the bare cavity frequency. So what I see is that at this frequency lining up with sort of the dispersive shift of the state I want to forbid, all the red curves are big, all the black curves are small. So step one here then, I want to drive my coherent tone for this measurement at the frequency to which the cavity would be dispersively shifted when the forbidden state is populated. Okay, that's choice number one. Secondly, right, I'm plotting this now with several different decay rates. So you can see how the decay rate matches onto the line width of the cavity here very clearly. If I want this to be big and these to be small, and I'm limited in terms of how these dispersive shifts lie, what I need is to make these curves narrow enough so that this peak is well separated from its nearest neighbor. So that means I now have some limitation on my line. I need my line width to be narrower than the gap between the dispersive shift for the level I'm trying to target compared to the next nearest neighbor.
Good.
Okay. So what we'll spend most of the rest of the talk wrangling with is what that means for the timescale issues involved in this scheme, right? Because if I limit my cavity line width, that's all well and good, but I'm also changing the speed at which my cavity pointer states can respond to whatever else is going on. All right, so here I'm showing just the ring up of the measurement strength to vacuum, and clearly as I make this narrower, I'm going to get better resolution of the measurement I'm doing, but I'm also slowing down my cavity, and that's going to have ramifications for readout. Okay, so the ideal situation then that I'm going to have, right, is if I can do this right, this pointer state for the state I'm trying to target will move away while the other ones will all just kind of stay stuck as close together as possible. Okay, this is what I'm trying to engineer, and that'll meet this, this requirement I want, that I'll have strong Zeno blocking of the transition of interest with minimal decoherence in the gate subspace that I'm holding below. Okay, so basically delta chi is going to be this gap between the dispersive shifts of interest, the peak I want in the next nearest neighbor for the rest of the talk, and I need that bigger than kappa by at least a factor 2 of 3. Order of magnitude would be great, but you don't need that much, strictly speaking. Okay, so there are 2 timescale choices we could then imagine doing this game. Either you accept that you're going to do everything very slowly. You make your dispersive gap here as big as you can manage by whatever means you can. That sets the limitations on your cavity line width. And then you say, well, I'm going to keep using this analytic measurement model, and I'm going to do everything as slow as I need to for that to be okay. Alternately, you can wade into the regime where you might have to because of decoherence times, where you drive your gate at a speed that's comparable or even faster to this cavity decay rate. But then you're going to start having to leave your sort of coherent analytic pointer state measurement model behind, and deal with something more complicated. Right, and then there's also this decoupling limit that people have written about where you forget it, your measurement's gone. Let's just get a sense with a qubit model of kind of what this looks like, right? If I'm plotting Q functions here. So if I drive nothing, no independent dynamics on the qubit, right? This is the model in which, this is the situation in which my analytic sort of coherent pointer state model applies exactly. And that'll stay approximately true for sort of modest drives. What I actually see here is an enhancement in measurement strength, though, as I sort of push into this non-Markovian regime. I'm not sure this is well understood, not by me anyway, but it's an interesting effect that perhaps explains some things we'll see in a minute. Right, and I can also see this sort of decoupling limit where I just go way too fast and the cavity can't follow anything the qubit's doing anymore. Right, and if I change my parameters a little bit, just so everybody's on the same page, I could turn this nice kind of readout situation that I would like to deal with into something instead, maybe like this, which is still going to dissipate some information you can see, but if you're trying to infer what these pointer states mean for the qubit, I think you're in for a hard time.
This is in the decoupled cavity limit on the right, is that right?
No, this is more in this sort of.
Oh, Don
This is in
Markovian limit.
this sort of, yeah. This is in the case where you're doing dynamics sort of comparable to. Yeah. And I know Justin knows, I think, a great deal about this since you've thought about sort of the machine learning models to deal with situations reminiscent of this. Okay, so back to the Zeno gate. Let's start with the very slow limit. So I'm going to use my coherent state model and assume that I'm doing my gate very slowly, right? So I can still use this coherent pointer states, Markovian approximation, all of that. Okay, so you can calculate your Zeno gate fidelity just with dissipation, and then again with see the improvement you get by actually using some measurement information. Okay, so just to guide you through this a little bit, right? The sort of the 90% fidelity is this purple. I'm plotting the ratio of sort of my dispersive splitting to cavity line width, and then the effective steady state strength versus the speed at which I'm doing the gate.
Right, your splitting is ratio of 60/40. Seems huge.
Yeah, so this is going deep into this is extremely demanding in terms of your dispersive shifts, or you're doing things with a very narrow line.
Is this delta chi for level pairs or the whole spread of levels?
This delta chi is between, to make this figure, we've assumed it's equal between the same excitation number,
Okay.
which is approximately, it's approximate. We assumed it equal and go on and scaling with excitation number.
Okay, so this is the per pair. Okay.
Yeah, this is, yeah, exactly.
Yeah, that's huge. So I'd expect like 2 or 3 to be more realistic than 20 to 40.
Right, so to get into this sort of slow limit, you're assuming, yeah, either you can make your dispersive shifts really big, or you can make your cavity line width really narrow. If you're sort of, right, so at the, stressing the limits of this, right, you can, this is a good enough model. This is sort of the edge of what you can do. You're assuming you're basically, you come out of the gate time for other realistic parameters of maybe like 20 microseconds or something on the edge of where this is at. Right, and that's getting you, even with measurement, a gate fidelity on the order of like 90%.
So Phil, I'm confused.
Okay.
Why are we having such huge dispersive shifts? Normally we will work with much smaller ones compared to kappa. What's going on?
Yeah, well, so we need, I mean, I guess in this case, really, we're working, you make your dispersive shifts as big as you can, but then you narrow kappa correspondingly to make the ratio big.
Yeah, so you want the narrow, you want this to be
The narrow,
big to have the narrow, to only target one thing.
right, so we're narrowing this, right, to isolate a very specific state, because we want to measure only the highest excitation number without decohering.
But then don't you have, then aren't you're outside of the bad cavity limit, so the usual assumptions of the measure model break down.
Yeah.
That's why I say usually you'd be around a factor of 2 to 5 for that ratio.
Yeah.
I think that's hard to get bigger than that.
Yeah, so this is why this was a challenging experiment, I think. Right, so they did,
And why isn't 2 to 5 good enough? Why do you have to go way so much larger?
it's really just to limit your, I mean.
Oh, so because you want to get above 90%?
Right, well, so part of what's going into these fidelities, right, is it's partly leakage through your Zeno block on one hand, and it's partly then the infidelity due to decohering your computational subspace while you do the gate, if you haven't isolated the
It
transition.
depends on the value of kappa you choose, right? If it is very small, then you have well separated ones, and then you can have high fidelity.
Yeah.
But at the same time, you like increase your gate time.
Yes.
Yes, so that's my point, is the narrower you make kappa, the more you increase your gate time to make any of the underlying assumptions here even vaguely plausible.
Right. Is there a reason you didn't extend that horizontal axis back towards 0 or 1?
Say again?
Is there a reason you didn't extend the horizontal axis all the way down to 1, which would be
Yeah, I chopped it here because there's an assumption implicit in even getting the expressions that are plotted here that these ratios are large.
Gotcha.
So whatever is being plotted here isn't even accurate anymore if you go back.
Okay.
Okay. So just for reference, right, here we're already talking about like 10% of the lifetime of a like state-of-the-art superconducting qubit. So when I say slow, that's what I mean. This is going to run into coherence time problems even if you could do it. Okay. So what that means then is we need to sort of wade into this, the shallow end of this more non-Markovian regime where your pointer states get weird and all that. So I'm plotting a wide variety of things here, which are, okay, these are my same 2 figures of merit, right? Proxy for Zeno blocking and the subspace coherence at the end of the game. So I can see, right, I'm plotting this as a function of the coherent input to the cavity, which is sort of the measurement strength, right? This is based on the coherent state model right here, which is not accurate for all the curves. We'll compare with simulation in a minute. Right, and all the different colors correspond to different line widths. So right at the fast end, we would usually like to work at. You can get decent Zeno blocking, right? But as you dial measurement strength up, your concurrence dies because you're decohering your subspace. On the other side, right, I can still get some Zeno blocking in a certain regime, but at some point I'm going to run into photon number problems. We'll talk about that in a minute. I haven't been able to eliminate in this case this resonator-induced phase, which is also applying something like a phase gate, like the Zeno gate, so it's therefore interfering with the Zeno gate dynamics we might want to isolate. Okay, so this is not necessarily a bad thing, but it is a competing effect occurring at the same time because of the way we're doing this measurement. If I compare with simulation, so this is assuming dispersive coupling still. These things are getting chopped at quite high photon numbers. So these smaller line widths are pretty much forbidden just because of the high photon numbers that would be needed here. So something interesting I see though, right, is that when I do plot these things, I get an actually better performance in the simulation for these very narrow line widths compared to the coherent state model here. So what that suggests is that maybe this non-Markovian regime is not all bad for this gate. More needs to be understood. Okay, but so this deeper case where we don't have a good analytic model for the pointer states may actually allow something here. Other than that, I'm limited in all the same ways my sort of coherent state pointer model suggests. And this is still for a relatively slow gate. The more I accelerate this, the more this is going to fall apart.
So, yeah. Question here, delta chi is fixed here, right?
Delta chi is fixed here. I'm using I think the same numbers I plotted.
Okay, so this red curve that you have there with tiny chi or tiny kappa.
Yeah.
That would correspond to a very large delta chi over kappa ratio.
That would correspond to a very large delta chi over kappa ratio.
So is this not just your other regime? This doesn't seem like it's in this Markovian regime.
Oh, I think it is because you're right. I'm fixing the gate time, which fixes my unitary, which is occurring faster than the cavity decays. But then also, right, as I increase the input drive to my cavity, I'm basically going to accumulate too many photons for the dispersive approximation to hold fairly quickly, right? Because I'm putting it in and it's not releasing photons fast enough to balance that out.
I see. So your resonances are well separated, but your dynamics are too fast for the cavity relaxation.
Yeah,
okay.
That's what we're getting down here.
Now I understand. Okay.
Yeah, that's what we're getting down here. Right. Whereas back here I have the measurement dynamics I usually want, but I don't isolate the subspace. I decohere too much.
Gotcha. Okay.
So there's sort of this sweet spot in the middle of this range here that's the best we can get right now with realistic parameters under this scheme, if you want. So, right, this is again this like 90-ish% fidelity or like 80% concurrence generation. Even in theory, without other decoherence sources, this is about the best I think we can do with dispersive coupling and dispersive shifts on this order. Okay. Right. So let me summarize a little bit of what we've seen in this exploration then. Right. So we can use the coherent state model up to a point, but it's only really even approximately valid for a very slow game. On the other hand, right, we can wade into this sort of non-Markovian regime, And there's quite a bit we might want to understand there in terms of distortion of the pointer states. How do you actually back out information? Right? How does your measurement strength depend on the interaction between the different subparts? There are plenty of further directions you could think about within the context of this gate, within the dispersive approximation, even even from the theory side. Never mind experiment. Right, so then people are working on various aspects of this, right? You can think about your measurement without actually making all of the dispersive approximations, use dispersive principles, but keep other terms in that are usually parasitic. You could try to model that. We could, of course, think about sort of shaping the time curves of the input drive versus the unitary we do a little better to sort of balance out trade-offs in a different way. You could imagine either suppressing the resonator-induced phase effect or doing a gate that sort of jointly uses the Zeno gate effect and the resonator-induced phase together to do something useful. And of course, you could think about feedback correcting this thing if you're actually collecting your measured outcomes. I think what I want to underline here is that a better understanding of these non-Markovian regimes would help all of the above. That is a broad point. I'll leave you with the only experiment to date on this Zeno gate. These are the main results. So you have, right, concurrence generation, about half the best I showed from the theory side, similar fidelities, and slight increases with heralding based on inefficient measurements. So I think what I want to highlight is, right, this is Shay's lab. Basically what they've done here, in my view, is maybe not yet useful from the purpose of using this gate for quantum computation, right? I mean, it's not even 1.9, but this is really great proof of concept of the general idea of the Zeno gate that we've introduced. And maybe with different sort of measurement strategies, one could do better, right? Clearly, if you had a way of making a readout with some intrinsic degeneracy, I mean, that's what we learned from the longitudinal case, you could, in principle, do much better if you switch over into that kind of situation. Okay, so I hope, explained a sort of multi-qubit entangling gate, scales well to many qubits in this paradigm, but you need to define sort of a degenerate measurement, and I think we can I hope I've introduced sort of many of the issues that arise when one tries to approximate that in practice. There has been experimental proof of principle for superconducting qubits, and one could think about how you might realize this with the different readout schemes that apply to other platforms. Thank you for your attention. I'd be glad to take more questions.
Phil, we have time for a few questions.
Yeah, I was just curious when you showed that experimental plot, what does the corresponding regime for this is like a Markovian?
So their dispersive shifts are similar to what I showed here. I want to say their kappa is I think this order. So they're at about the best sweet spot you can back out from theory. What they're doing here, right? I mean, of course, they're limited by other decoherence times, which aren't great. They're doing the gate here about an order of magnitude faster than that plot I showed because of their decoherence times. So that's bringing in additional issues that are, right, sort of pushing this concurrence generation down. The other thing they're doing is they're actually using two measurement tones at different frequencies in an effort to partially cancel the resonator-induced phase effect to isolate the Zeno gate effect specifically. So those are some modifications from the theory I showed that are going into getting this experiment.
Any questions on the Zoom? No? Any other ones? Okay, let's thank Phil again for a nice talk.